Hey everyone, welcome to the video on finding the center of mass of 2D laminas, and we're just going to do some examples in this video. Here I have a sine and a line, and I'm going to go ahead and find these F and G, and then where is that center of mass going to be? So this sine function, we got to manipulate a little bit. So it looks like it has this amplitude 1/2 right there. Period is 2, and just in case you've forgotten some of your trig, if the period is 2, remember the period is usually, go and just write it right here, 2 pi over k. You can also think of k as 2 pi over the period, so sometimes that will also help. K is 2 pi over the period, and in this case, if we know the period is 2, we'll just get 2 pi over 2, which is going to be 2 for this one, so, or pi. So I'll just write it out. K is 2 pi over our period 2. It's going to be a pi, and this is the value that gets multiplied by the x in the sine function. So far we have this 1/2 sine of pi x, and there's no left or right shifts, so we don't have to worry about that. There's no vertical shifts, so don't have to worry about that, so we'll call that function good. G of x, this is just a line, looks like it's got a slope of -1/2, so my rise -1, run 2, so -1/2 x, and then looks like y-intercept is -1, so we'll put a -1 right there. Sometimes that can be the trickiest part of the problem. If you don't have functions given, just coming up with those functions. After that, it's just a matter of applying all the usual formulas. So for the my, don't forget we're going to do this integral of, and rather than rewriting all this in there, I'm just going to put f minus g, and we'll go ahead and calculate that using Desmos. So I'm not going to go through the calculations, these integrals by hand. You certainly could do those. These aren't too hard to do, but that's not really the idea I want to get through here. It's just setting these up. So we got 0 to 2 as our bounds, so we'll go 0 to 2. And right now this is just the area, so don't forget that f minus g is multiplied by x. So the area would be okay to calculate, but as soon as I multiply by that x, some of these are going to get a little tricky, and depending on the order of the class, if you haven't been through integration by parts, you're really not going to be able to do this x times 1/2 sine pi x. So for this one, we're just going to calculate this with some technology using Desmos. So we'll do that in a second. Mx, we'll go ahead and write that out. So this is integral 0 to 2 of, and then again, we're going to put that 1/2 times squared minus g squared right there, and then our dx. And then we'll just scroll down just a little bit here. So area, so this is going to be integral 0 to 2 of just f minus g, and then my dx. And we'll go ahead and approximate those. So some space here to approximate these. And I've done a couple videos before on how to do this with the TI-84 or with Desmos. We're just going to use one of those this time. So if I bring up Desmos and type in our functions, and I'm just going to use y1 and y2. If you want to use f and g, f of x, g of x, that's fine, but sometimes it's easier to just type in y1, y2. So for this one, we had 1/2 times the sine of pi x, and for pi, you can just type pi, and it'll change it. So we got pi x right there. For y2, we're going to type in that -1/2 times x minus 1. So those right there are my functions, and between 0 and 2 you should see that kind of matching up with the shape that we had before. Now the nice thing here is that when I integrate, I can integrate 0 to 2, and I can just type in y1 minus y2. Probably need some parentheses here, maybe not. We'll just put them anyway. Dx. So this is going to be my area. So I'll go ahead and put in 3 for my area. Go ahead and copy that. We'll paste it. The other one we want, right, the mx, just has an x in front of there. So this will be my, my, not mx. So that'll be my. And then the other integral, so I'll paste that again, is going to be, and the 1/2 you can put either in front or in the integral. It's not really going to matter if you're just calculating these out using technology. But I do want that y1 squared, and I also want the y2 squared. All right. Now, one advantage of doing it this way is that you don't have to worry about, say, misplaced parentheses or things not grouped appropriately. So let's take those y1, y2. So you can also do that in the TI using the variables button. As long as you have your y1 and y2 in the graphs defined, it's a lot easier to calculate these out that way. So I highly recommend that. So we'll go and copy down these values in the worksheet, and then we'll go ahead and divide those out. All right, so I've got this MYMX and area written down here. The centroid, remember, we're just going to divide those out. So we want to take that 3.0150 with other decimals. If you want to be more accurate, you can include those. We're going to divide that by 3. The negative 2.2083 repeating. Again, you can kind of include as many 3s there as you want, and then we'll divide that by 3 as well. And normally for these, we'll go ahead and divide those and just get an approximation. 2 to 3 decimals is usually okay for that. So for this one, I've got 1.005 and negative 7.361. And I do recommend a lot of times going through and just double checking to make sure those numbers make sense. So 1.005, that's going to be really close to 1, somewhere just to the right of 1, not very far away, probably actually visually pretty much on that line. And then the negative 0.73, that's almost 0.75, so about 3/4 down, negative direction, so probably somewhere in here ish. So we're looking probably right there as our center of mass. So that should make sense in terms of the figure. So you got kind of these mass times distance areas that should kind of balance out. If you take the mass here times the distance, the mass here times the distance, and if you were to calculate it all the way out for little individual pieces, you should see them balancing around this point. And in fact, if you were to take a shape that was actually created that was flat, uniform density, and balance it on a point, as long as you put it right there, it should balance completely flat at that point. All right, let's go and take a look at one more and actually have you guys try this one. So go ahead and try this one, pause the video, and I'll go ahead and write down the answers here in just a second, but pause the video, try it, see what you get for the center of mass. All right, so hopefully you've got some numbers that look like this. So our parabola here is shifted to the right 2 and up 4. So we got the x minus 2 quantity squared plus 4. We got the negative in front since it's up down. And You could also do something like with the factors x and x minus 4 with a negative, again, because of it opening down. It only goes 1 unit left or right when you 1 unit down when you go 1 unit left or right. So it's just a -1 in front, not any other sort of coefficient. So just looking at transformations with that parabola. The sign, again, you got the sign of just a period change, so pi over 2x with that one. And these are the numbers that you get. 10.6 repeating, 23.8798, 16.06 repeating. And the nice thing about Desmos is you can just change the functions and it'll give you the same numbers. You do want to change the bounds as well in those integrals, but it's not a lot of extra calculation work other than now I have to divide those out. So that is a nice thing. If you're doing a bunch of these, you can just leave this up, change your functions, change your bounds, and it goes pretty quickly once you get the hang of it. Let's go ahead and take a look at the final answer here. So that's going to be 2.24, 1.51. Once I divide out the my with m and the mx with m. All right, one last one I'll talk about, and I'll just talk about the idea of this one and then maybe throw up a few calculations over here on the side. So for this one, we got a natural log function going up here, but we do have a hole in the shape. And what you want to do is treat this like you did the composite shapes earlier. So I'm going to think of this as a big natural log type function and a rectangle that I'm going to subtract out of it. So I want the center of mass of both of these pieces. And I'll go ahead and just write up the calculations for the center of mass of the natural log over here on the left. Alright, so here's the calculations I get for the natural log function. So that would be all the shaded area, including inside this rectangle right here. So if it were all shaded, I would get this 2.4883 and 0.6, which is about right there. And for the rectangular hole, I get 3.5, 1.75, which is right there in the middle, and mass, so this is again just a half a unit height, so 1/2 times 1, which is half. So now I just want to combine those, so I need to do a new mx, my calculation, and I'll go ahead and put those down here. We're just going to take them, remember the mass times the distance for these guys. So how far am I from the x-axis, how far am I from the y-axis, just those mass times distance calculations for the moments, and adding up the total mass. Alright, so combining these mass times distance for the natural log piece, we get this 4.0472 times the 2.4883. So there's that mass times distance in the x minus mass times distance for the rectangle. Same thing for the mx, and then the m, just this mass or area minus that kind of mass area. And dividing out the my and the mx by m, we get this 2.35 and 0.44, which is about right here, which if you think about it makes at least a little bit of sense. I have this area I'm taking out, which has a bunch above this point, so that's gonna lower the center of mass, and it is gonna shift it left a bit, just because this hole is now removed, so I have more mass on the left side. It's going to drag the center of mass that way. Again, it's not a huge distance away, so it's not moving a ton, but it does move a little bit. So anyway, that's the idea of combining composite shapes, even when maybe they're not all rectangles or circles or things like that, but you just compute center of mass the same way you did before, and just use those point masses on each shape as you go. All right, that will do it for center of mass.